Gill Nye, the science guy.
Jill, Sarah, Math, Soft, Drew. Gill Nye, the science guy. Chemistry rules. Gill Nye, the science guy. Atoms are the building blocks of matter.
Protons, electrons. Gill Nye, the science guy.
Jill, Sarah, Math, Soft, Drew. Sarah, Math, Soft, Drew.
Caution. Before starting a lab in the laboratory, make sure you have your goggles. In addition, do not drink chemicals in the laboratory. Here we have a stone. If we break the stone up into two pieces, we still have two blocks of the same piece of stone. As we continue to break the stone up into smaller pieces, we are eventually left with one small piece that cannot be broken up anymore. This is what we call an atom. Democritus' theory is an idea branching off of this experiment. Democritus was a very simple man, therefore he did not have much technology to prove his idea. He left his idea for other scientists in the future to prove. Democritus' theory states that matter is made of indivisible atoms that move in a void. They cannot fuse together, but they can combine in clusters and break away. Their physical structure determines certain properties such as texture, color, and taste. For example, the texture of an atom can determine taste, such as when an atom is pointy, which causes it to taste sour. But what other discoveries and scientists helped Democritus to get to this point? Let's take a look at a blast from the past.
Blast from the past!
This is young Democritus and Leucippus. Leucippus was also a Greek philosopher, and he led Democritus to believe the same theories that he believed by teaching him.
This is what I call atomism. It states that all matter is homogeneous and made up of tiny, indivisible particles. These particles created the world by colliding together to form a whirling motion.
Democritus took this main idea that Leucippus had introduced to him, and he created even more in-depth ideas. He named these small particles that Leucippus talked about atoms, which mean unchangeable. That was a lot of information to take in. Why don't we freeze for a fun fact?
Democritus was also known as a laughing philosopher because he was always found smiling on the job.
Aristotle and Plato disagreed and said that matter was composed of four elements: fire, air, water, and earth. This caused Democritus' theory to wait almost 2,000 years before it was rediscovered by Dalton. Why don't we take a look at Dalton's theory?
Oh, hello there, children. Today, I'm going to be talking about Dalton, John Dalton. Even though he started studying atoms after Democritus, he is credited with the first atomic theory. It consisted of 5 main parts. Number 1, matter is made up of atoms that are indivisible and indestructible. Also, all atoms of an element are identical. And atoms of different elements have different weights and different chemical properties. And also, atoms of different elements combine to form compounds. And finally, atoms cannot be created or destroyed. When a compound decomposes, the atoms are recovered unchanged.
Blast from the past!
This is Dalton reading about Democritus' theories.
Wow, this man is so cool and smart. I wonder if there's anything else he didn't actually solve. While all atoms of an element were identical, like these two $20 bills, different elements have atoms of different size and mass. Dalton's atomic theory also stated that all compounds were composed of combinations of these atoms in definite ratios. Dalton also said that chemical reactions resulted in the rearrangement of the reacting atoms. He used experiments with gases to prove this. He found that water absorbed carbon dioxide better than it absorbed nitrogen. Dalton hypothesized that this was due to the differences in mass and complexity of the gas's particles. Carbon dioxide molecules are heavier and larger than the nitrogen molecules.
Hold up, all this talk about this cool guy Dalton, and we don't know anything about him?
Oh yeah, you're right. Dalton actually came from a poor family and was a Quaker. He was so smart his whole life that he actually started teaching, not learning, teaching at a college at the age of 14.
Whoa!
Whoa! Oh my
that's
god!
sick.
Whoa!
Yeah, cooler than you. Dalton basically took Democritus's ideas and took them further. He may have been a super smart person all his life, but he was not always correct. His theory that atoms were indivisible would later be proven incorrect by a man named J.J. Thompson.
That's me.
Now we're going to be talking about J.J. Thompson.
What up? It's JJ. It's Mia. Think about a chocolate chip cookie real quick. Delicious, yes, but also used as a scientific model by English physicist J.J. Thompson. He believed it was representative of an atom. The atom was like a chocolate chip cookie filled with positive charges, and the chocolate chips, which were the newly discovered negative charged particles, which we now know as electrons. By the way, he discovered those too, along with isotopes.
Freeze for a fun fact. In 1908, J.J. Thompson was knighted by King Edward VII.
Thompson's discoveries greatly contributed to our knowledge of the atomic structure, so he won a Nobel Prize in Physics in 1906. He taught many students after his success, and they went on to make significant discoveries as well, like the discovery of the proton and internal structure of the atom. In fact, our next scientist, Rutherford, was mentored by JJ.
Yeah. Now it's time to learn about Ernest Rutherford and his groundbreaking atomic discoveries. Rutherford was a British New Zealander who discovered the structure of the atom. He followed in the footsteps of his mentor, J.J. Thompson, to research more about the atom and its properties. His major discovery about the atom was found through his gold foil experiment. From this lab, he discovered the atomic structure, which contains a small, dense, positively charged nucleus with electrons evolving around it.
Blast from the past!
Rutherford is now in his lab planning his experiment with his assistants, Hans Geiger and Ernest Marsden.
Now, my teacher, J.J. Thompson, has created a very interesting structure of the atom with his plum pudding model, and I think we should test that out. How should we do it? Hans? Ernest, what do you think? Oh wait, I got it. I will use a beam of alpha particles which are encased in a lead container, which will look like this. I will direct this beam of alpha particles to a piece of gold foil, and according to Thompson, some of them will go directly through it and others will deflect from it. Because the particles are heavier and have more energy, they will deflect off the positively charged gold atoms. These beams will go directly through the foil and reflect onto a fluorescent screen. Great, time to try it. Wow, I didn't expect this. Though most of the particles went directly through like Thompson said, others were deflected and a few even rebounded from the foil. But why? I've been thinking about this for a while, and maybe the whole structure of Thompson's plum pudding model was wrong. I think the atom is mostly made up of empty space, where the electrons revolve around a small, dense, positively charged nucleus that contains all of the atom's protons and neutrons. In this experiment, most of the beams passed through the empty space of the atom, while the ones that got deflected hit the nucleus, and the few that rebounded hit the exact center of the gold foil nucleus. Now it's time for a fun fact.
Did you know that Rutherford is on the 100 bill New Zealand note?
Rutherford's nuclear atom is still used as a structure scientists used for the atom. Though Rutherford made groundbreaking discoveries, it still had flaws, which were later discovered by Niels Bohr, who is now going to be discussed.
Oh hey, it's Jillian. I didn't see you there. Let's talk a little bit about Niels Bohr. Bohr was a Danish physicist who attended the University of Copenhagen. At one point in time, he was even the student of Rutherford, which is funny because Bohr ended up proving Rutherford wrong, but we'll get to that. Bohr even won a Nobel Prize in 1922 for his great work. Bohr created an atomic model that is also commonly called the planetary model. But why? I think we need to take a trip to space to understand that.
As you can see, the sun is the center of the solar system, and the planets orbit around the sun in a specific fixed way. This is just like Bohr's theory, as the represents the nucleus, and the electrons represent the planets. Bohr's model shows an atom with a positively charged nucleus surrounded by an equal number of electrons that travel in circular orbits around the center. His main idea and discovery was that electrons travel in certain orbits depending on their specific energy and size. If they didn't, the atom would be unstable. Bohr also used the idea that electrons can only gain and lose energy by jumping between different orbits, absorbing or giving off electromagnetic radiation in the process. But how did Bohr come up with this theory? Let's take a look back in time.
Blast from the past!
None of this seems right. There was Rutherford's gold foil experiment. It caused him to create this model. But that atom would be unstable because it shows the electrons moving on a curved path, which would produce electromagnetic radiation and a loss of energy, causing the electrons to spiral inwards and hit the nucleus. But there's also Max Planck's quantum theory.
My theory is that energy is only emitted or absorbed in certain defined amounts, which are proportional in magnitude to the frequency of the radiation it represents.
This makes perfect sense when applied to the electrons. The electrons in this case must have to be in a certain orbit around the nucleus, depending on their specific energy, and also must be able to only transfer energy in specific amounts, perhaps by jumping from one orbit to another. This jumping would then have to release or absorb radiation to keep the proportion of magnitude to the frequency of radiation, according to Planck's theory. Wow, that was fascinating. Now time for the best part. Fun facts about Bohr. Lightning round!
Bohr set off multiple explosions in the University of Denmark.
Bohr made his own glass tubes for his experiments.
Bohr had 6 sons, and one of them even won a Nobel Prize, just like his dad.
And fourth, Bohr even has an element named after him.
Bohrium!
Niels Bohr sure is interesting. While his model and theory were proven to not be completely true, they had a very large influence on the development of the standard model of particle physics, which was a model that focused on the electron cloud. In addition to this, forms of the Bohr model are still seen in classrooms to this day. You probably see or draw one all the time in your science class. Anyways, thanks for listening about Bohr.